Alright, let's start with lesson 2, the equilibrium expression. Now that we've looked at some basic ideas of equilibrium, understanding that when a reversible process occurs, that the forward and reverse reactions, when they have established an equilibrium state, that those two processes, the forward and backwards process, are occurring at equal rates. Now what we're going to do is we're going to dive into a lot more in depth into the equilibrium. But these principles in lesson 2 are absolutely critical that you understand, especially the equilibrium expression and the equilibrium position that we started talking about in lesson 1. Alright, so what I have in your notes here is a basic symbolic reversible process where we have our reactants here and our products on the other side of our double arrow, which represents, again, the double arrow represents that there is a reversible process or reaction that's occurring here. Alright, you can erase all of this. So what this is saying is reactant A is going to react with reactant B. Now the little a and the little b represent the coefficients for A and B. And when A and B react, they will form products C and D, which have subscripts little c and little d. Now, what we're going to do is we're going to learn how to write what is known as the equilibrium constant expression. Now, this expression is vital in our study of equilibrium. You're going to be writing equilibrium expressions quite a bit in the next several units that we go through. That includes this unit in acid and bases, as well as precipitation types of reactions and oxidation reduction. Okay, so let's get started with the equilibrium expression. Essentially, the equilibrium expression is where we take the concentration of the products at equilibrium, and that's what the EQM means, is equilibrium concentrations, and we're going to raise it to a power, okay? And the power is the coefficient of that reactant or product. So as you can see here, we're going to take the concentration of one of our products, which is D, and we're going to raise it to its coefficient, which is little d, and we have brackets. Remember, brackets mean that the concentration is in molarity, and those concentrations of molarity are going to be at EQM, equilibrium concentrations. Okay, so again, we're going to take our product concentrations raised to the coefficient powers as powers and divide that by the concentrations of our reactants, and they're going to be raised to their coefficients as powers. And again, they're at equilibrium concentrations too. Now, this division problem is equal to a value known as Kc. Now, Kc is known as the equilibrium constant. All right, equilibrium constant, Kc. All right, this is not the rate constant that we learned in kinetics, and that's why we use a subscript c to indicate a difference between the rate constant that we learned out in the rate law and the equilibrium constant that we see in the equilibrium expression using Kc. All right, so don't get those confused. Now, a couple of things to note and understand about the equilibrium expression, and this whole thing is known as the equilibrium constant expression. You can never, ever put liquids or solids into the equilibrium expression, so make a note of that. You'll never put solids or liquids in the equilibrium expression. So really, what does that leave? That leaves aqueous solutions and gases. Those are all appropriate to put into the equilibrium expression. All right. Now, a few other points. The equilibrium constant, Kc, has a fixed value for a particular reaction at a specific temperature. And I want to really emphasize this specific temperature. It means that Kc is dependent on the temperature. If the temperature changes, so does the value of Kc for that reaction. Very much like or very similar to the rate constant in the rate law that we talked about in kinetics, which is also temperature dependent. So the only thing that can change Kc then for a reaction is the temperature if it changes. So in other words, Kc for a reaction is temperature dependent. All right. Let me write a quick equilibrium expression for you here. Oops. I'm going to erase all of this and write a real expression. So let's say we have a reaction of H2 gas plus iodine in the gas state, and this produces a reversible process. So I use the double arrows of HI, which is also a gas, and we balance the equation. It should be 2 HIs, and the rest are have coefficients of 1 each. Okay. Now notice all of these states are in the gas, so that we can write an equilibrium expression for these particular substances. So I'm going to write that Kc, our equilibrium constant, is equal to, remember we're going to do the products first, so we're going to do the concentration of HI, and we're going to raise it to the second power because the coefficient is 2, divided by the concentration of our product or reactants, which is H2, and it's to the first power, and I2, and it is also to the first power. So that's how we would write the equilibrium constant expression for this particular reaction. Okay, so write that down in your notes so you have a good example of this. And remember, one more time, the only thing that can change Kc, the equilibrium constant, is the change in temperature. All right, so let's go now talking about the equilibrium position again. Remember, we talked about this in lesson 1, so let me recap a little bit. The equilibrium position is determined by which reaction, the forward or reverse, is more favorable thermodynamically. If the forward reaction is more favorable, then essentially we're going to have a higher product concentration than reactant concentration when equilibrium has been established. However, if the reverse process is more favorable thermodynamically, then when the process reaches the equilibrium state, there's going to be a higher concentration of reactant than there will be a product. Okay, so that should recap from lesson 1. Make sure you understand that. That's so important. Okay, now the equilibrium expression, specifically Kc, the value of Kc, can help us determine the position of the equilibrium when we've reached an equilibrium state. So the magnitude of the equilibrium constant gives us information about how far the reaction goes at a particular temperature, but not about how fast we achieve the equilibrium state. Okay? So in other words, Kc has nothing to do with how fast the reactions occur, both the forward and the reverse reaction. Instead, Kc tells us where the equilibrium position is. Is it product favored or is it reactant favored? Okay? And so this is how you can tell. If Kc is greater than 1, then we find that the reaction is going to be product favored, and we use this terminology that the equilibrium lies to the right. Now, we're going to talk about that a lot. We're going to use that terminology. You're going to write that terminology on quizzes, exams, or whatever, homework. When we say that the equilibrium lies to the right, we are saying that it is product favored. There's going to be a higher concentration of product than reactant when the equilibrium state has been achieved. However, if the Kc value is much, much greater than 1, we're talking on order of magnitudes of times 10 to the 4th, 5th, 6th, or higher, then we almost will say that the reaction goes to completion. In this case, there's not really much or any reversibility that's occurring here. So we're simply saying that all of the original amount of reactant is converted to product. And these are the types of reactions that we have been really focusing on the entire year until this point, where we've looked at Kc values being really large values. So the reactions that we have looked at go to completion, and there's been no reversibility occurring. So again, when Kc is that large, it's a one-way forward reaction. No product is reacting to reform reactants at all. So we won't have an equilibrium being established, really, as what we're trying to say here. However, if the Kc is small, smaller than 1, then we're going to say that the reaction is more or less reactant favored, and that means the equilibrium is going to lie to the left. So that means there's going to be a higher concentration of reactant than there will be product at equilibrium. So the reverse reaction is the thermodynamically favorable reaction in this situation. Now, if Kc is so super small, we're talking an order of magnitudes of times 10 to the negative third power or lower, then the reaction hardly goes at all. All right, there's not going to be much of a reaction that occurs under those conditions, at least in the forward direction. So it just simply means that the reverse reaction is very, very dominant in the one that we're going to mainly see in nature because of the thermodynamic conditions make it more favorable. All right? So really, equilibrium position has a lot to do with the principles of thermodynamics, which of these reactions, the forward or reverse, is going to lead to an increase in entropy in the universe. All right? And Kc gives us that kind of information. All right? So hopefully this makes sense. If not, re-listen to this video a couple of times until it really solidifies into your mind of these kind of ideas. All right, so what we're going to do now is we're actually going to put some math into this. We're going to actually figure out how we can calculate Kc given some concentrations at equilibrium. All right, so what we have is a problem that's in your notes here, and it basically reads here is that a mixture of Hi, H2, and I2 gas are in a reaction vessel, and they're going to be allowed to reach equilibrium at a temperature of 723 Kelvin. Now, don't get caught up when you see the temperature in these equilibrium problems. It just basically remember that the Kc value is temperature dependent. So they're always going to list what the temperature is of the reaction so that you understand that at that particular temperature, this is what the Kc value will be. You don't really need to do anything with temperature at all. It's just there as a reference, more or less. Okay? So here is the reaction that we're looking at, and it is a reversible reaction according to the way it's written because of the double arrows. All right? Now, the problem asks the equilibrium concentrations are listed below. Okay? So that means that right here, are the concentrations of the reactants and products when equilibrium has been established. This is not the starting reactant or product concentrations. These are actual equilibrium concentrations, and that is important to understand because sometimes we don't start with the equilibrium concentrations. We start with the actual original concentrations of the reactions. But here, because we have the equilibrium concentrations, it makes this problem very easy and straightforward. All right. Now, we're going to calculate the Kc value for this reaction at this temperature. All right. So, to do that, I need to write out my equilibrium expression for this reaction. And that's really the first thing you should always do when solving an equilibrium problem is write out the equilibrium expression. So Kc is equal to, remember, the concentration of the product over the concentration of the reactant. And we need to square that because of the coefficient is 2 there. All right, and this is simply really going to equal, and we can throw in, remember that these concentrations are equilibrium concentrations. So we're going to throw in the equilibrium concentrations. We have 6.33 times 10 to the minus 4. You know what, I'm going to run out of room. So I'm going to actually erase this and try to make this even smaller. Okay, so 6.33 times 10 to the minus 4 times our iodine concentration, which is 1.23 times 10. Oops. Just write out minus 3 there, bracket that, okay, all over our concentration of our HI, which is 2.50 times 10 to the minus 2. Hopefully you make this a little bit nicer in your notes. And we're going to square that. Don't forget to square it, very important. So you work out the math and multiply and then divide, make sure you square. And you should get a Kc value of 1.25 times, oops, I'll write that a little bit better, 1.25 times 10 to the minus 3. Oh, by the way, units for Kc. Forgot to mention this. There are no units for Kc. Kc is unitless. You can, thank me later for that. So we don't have to worry about units whatsoever. Okay? So the Kc value for this reaction is 1.25 times 10 to the minus 3. So what does that tell us? Well, it tells us that Kc is less than 1. Okay? Less than 1. So where's the equilibrium position? Well, since it's less than 1, it should be reactant favored. Therefore, the equilibrium position lies to the left, right? And you should be able to recognize that from here on out, where the equilibrium position is once you know what the value of Kc is. Always be thinking that in your mind. Where does the equilibrium lie? Is it reactant favored? Is it product favored? All the time. That's going to help you to understand the problems that you're going to be looking at with equilibrium from here on out. All right? All right, so let's look at a second problem. This is going to be a little bit different. All right? I'm going to introduce to you a method of solving equilibrium problems that I like to call ICE. Most of us chemists do. ICE. ICE. Okay? What does ICE stand for? Well, I stands for initial concentrations C stands for change. In concentrations. And E stands for equilibrium. Oops. Equilibrium concentrations. Oops. Fill that in. Okay, so initial, I, change, and E for equilibrium concentrations, ice. Okay, now ice is going to be a very important way of solving problems for the remaining part of this year as we look at many types of equilibrium systems. All right, so I'm going to erase all that because I'm going to set up my ice problem. Now, I would recommend that when you set up an ice problem that you do so underneath your chemical reaction. So if you want to rewrite your chemical reaction, do so. That's what I'm going to do. Okay. So what I first probably should do is write my equilibrium expression, like I said before. So Kc for this reaction is equal to the product, which is Hi squared over H2 and I2. Okay, so what does the problem ask us to do? It says that we have a closed system, and initially the concentration, so the initial concentrations, that means when you see the word initial, that means the starting concentrations. So these are concentrations that are not at equilibrium at all. This is what we begin the reaction with. So the initial concentration for hydrogen is 1.000 times 10 to the minus 3 molar. For I2, it's 2.00 times 10 to the minus 2. And this reaction is going to take place at 448 degrees C, and it's going to allow to reach equilibrium. Now, we do not know we do not know the concentrations at equilibrium of H2 and I2. However, it does tell us that the equilibrium concentration of Hi is 1.87 times 10 to the minus 3 molar. All right? So we have the equilibrium concentration of Hi, but not of our two reactants, just their initial. All right? So we need to calculate Kc, but we can't calculate it directly like we did in our first example problem, because we need to figure out the concentrations of H2 gas and I2 gas at equilibrium before we can do that. All right? So this is where ice comes handy. So essentially I'm going to make a table here. I'm going to actually make my table so. I'm going to put some lines down like so, and make a nice table. Now I'm going to put I, C, and E, okay, my ice table. So initially what goes up in these top boxes is the initial concentrations that we're going to start out with. So initially for hydrogen we start out with 1.0, and I'm running out of room, so you can put all the zeros into your box, times 10 to the minus 3. And for I2 is 2.00 times 10 to the minus 3. And for our initial concentration of Hi, well, how much product do we originally start with in a reaction? Well, 0. We don't have any product, so it should be a 0 concentration there. All right, now the change in concentration. We don't know exactly, and we don't know what the equilibrium concentrations are, except for we do know the HI because it was given to us. So 7 times. You know what I'm going to do? I'm going to use a different color to represent our equilibrium concentrations. All right, so you can kind of see what we're doing here. So 1.87 times 10 to the minus third was our initial equilibrium concentration, is our equilibrium concentration for our product. Okay, well, what about the change? Well, we can figure out what the change of a concentration is for our product HI, because we went from 0 to 1.87 times 10 to the minus 3. That means that our product gained 1.87 times 10 to the minus 3 moles per liter. In other words, it gained that amount of concentration during the course of the reaction. All right? So, we're adding here. We're going to put a plus sign because it's gaining. Okay? So, how can we figure out the change that occurred for the reactants during the course of this reaction? Well, we can use the stoichiometrical ratios in our equation to kind of help us out. So remember that we are forming twice as much HI as we have reactant because they're both ratios are 1 to 1. All right? That means that in reality, we should have half the amount of concentration of H2 and I2 compared to our product, which has a ratio of 2 to 1. So that means that we can take our change in concentration of the product and divide it in half. And that would give us our change in concentration of our reactant. So what that would entail would be negative 0.935 times 10 to the minus 3. Okay? So that, all we're saying is we're taking 1.87 times 10 to the minus 3, and we're going to divide that by half because of the ratio. All right? So that gives us the change. And so when we find that we subtract the 2.00 times 10 to the minus 3 from our change, what we have left at equilibrium then for our I value, or I2, is 1.06 times 10 to the minus 3. Okay? Molarity concentration. So now we have 2 of the equilibrium concentrations. So our last one, we're going to get rid of a negative amount. Okay, that's because we're losing. Remember, the reactants are initially losing reactant concentration, so they're 0.935 times 10 to the minus 3. I'm sorry, this looks kind of messy. All right, you get the idea. And that value, again, is half of the change in our product because of the ratio of 2 to 1. Okay? So when we subtract the two values at equilibrium, we should have 0.065 times 10 to the minus 3. Okay? I'm just going to leave it into the negative 3 power. All right? So now, with our ice values, what that leads us with is the equilibrium concentrations. And now that I have those equilibrium concentrations, I can plug it into my equilibrium expression and solve for Kc. So that's what I'm going to do here. I'm going to take my concentration of HI, which is 1.87 times 10 to the minus 3. And I'm going to square that because of my 2. So again, I'm just using these equilibrium concentrations. Divide by our H2 equilibrium concentration, which was 0.065. Oops, she used the power. 5 times 10 to the minus 3. We're going to multiply that by 1.06 times 10 to the minus 3. Right, so we take our product's concentration, square it, and divide it by the reactant concentrations, and that will give us our Kc value. And I calculated the Kc value. I'm going to kind of squeeze this in because I don't have a lot of room here, of basically the Kc is equal to 51. Okay, so the Kc of this reaction at 448 degrees C is 51. All right, so that tells us that the Kc value is essentially greater than 1. And if the Kc value is greater than 1, then our reaction is going to be product favored, and the equilibrium is going to lie to the right. Okay, so remember, we have to think equilibrium position here too. So we're going to say Kc is greater than 1, and so it's product favored, and the equilibrium lies to the right. You might want to write that down to remember that. All right, so what I want to do is I want to stop here with this lecture video. We have another part to lesson 2, the second part, which you should watch, but this is going to be the end of the first part of this lecture video. Make sure that you really understand your notes. Rewatch this video if you need to. There's some important concepts or ideas that you need to take away from part 1 of lesson 2. Okay, so that is it for now.